for the header files we discussed, and then we are including these libraries which are required. Then these input files, as we said that we will need two input files, plist.txt and ptrace.txt. so we are assigning that input files to a string variable list and trace, which we will use it further. Then our main memory size, we are defining it as 400. Our main memory size is 400 for now. And then we are defining some variables like a register and instruction register, which are 4 bits, and then instruction counter. How many instructions are required? For that we'll need instruction counter. Then while running the program, we took the input from the user, that which algorithm to implement. To store that, we are defining a string called algo. Then we have some important variables which will be required in our program. So the first is p size. It is a vector of integer type vectors. So means that it will store the size, means all this plist.txt. This information will be stored in this p size. See, showing process id and its size, process id and size. So the plist.txt info will be stored in p size vector. Then we have ptrace. Now the information from ptrace.txt will be stored here. Again it will be the process id and then the memory location which that process will require sequence wise. Again it is a vector of integer type vectors. Then we have process list. Now process list is a vector of processes. In this plist.txt we have declared we are going to give input 5 processes. So this vector will contain 5 elements. Each element is a process. And then now each process contains a page table, process id, the size, the name pages. So this all information will be stored in this process list. Then for all this process we need a main memory. Virtual memory means the extra memory. So for that first we need a main memory. So main memory means also, it is also in the form of pages. We call it frames or pages. So we are defining a main memory. It is a DQ of pages. DQ means double-ended queue, means we can remove or add elements from both the front and the back side of the queue. So it is a DQ of page type. And then we have our virtual memory. Virtual memory is a vector of page types. Now virtual memory also contain different pages, so it is a vector of pages. Then we have a integer called page swaps. Initially we are defining it a value of 0, means whenever a page is swapped from the main memory to virtual memory or vice versa, so we will increment this counter. It is like a counter. Then we have our FIFO, means algorithm functions, FIFO and LRU. So we'll discuss it later on. Let us go towards the start of the program. Now whenever a program is run, the main function is called first. Then in this main function we are calling a load function. Then this here the load function is defined here. The load functions simply takes the input from the user, which algorithm to implement, stores it in the algorithm string, and then calls the execute user program function. Now in this function, execute user program function, what it does, it calls our virtual memory functions, passes it 4 parameters: list, trace, 5 and algo. Now list is our first input, that is we have stored it in the earlier list plist.txt. Then we have trace. Trace means ptrace.txt. We have declared these defined these variables at the starting. Then we have 5 is the page size, which I discussed it earlier, that we are giving page size as 5. And the next is the algorithm, which algorithm to implement, which it is, we are taking it from the user. Then this function will be called, means the virtual memory function will be called, and then the program done will be displayed. Now what happens in this function, we'll discuss that. See, here the virtual memory function is declared. The argument string a, b, c, d, these are the arguments. Then virtual memory called. Again we are declaring some variables which are required for our function. So the first variable is size of pages. It represents the size of each frame here, which we are going to take it from the user. Then page replacement algorithm, again we are passing this as an argument. We are going to store that in this stream. Then a iString stream is stored to, it is a string stream object to convert the arguments to string, these arguments to string. And then we have argument variables like the process ID, process memory size, and the process memory location. Process ID for these IDs, and then process memory size, these sizes for each memory, and then process memory location, these memory locations which they will require. And then initialization variables, we will have to initialize the main memory frames, means the number of page frames in main memory, and then the number of page frames per process. So for example, if total we have 100 memory frames, and from that, and we have 5 processes, then 100 divided by 5, each process will get 20 frames. So we have declared these variables here. Now here if stream input 1 a, if a means here this a is declared, then we are storing it in 1 if stream. And then if it is not set, if we are not passing it, it will give a error, please input a valid plist file and return this function. Then if it is set, then from that it is a file stream. Now in the list we have stored this file name, so we are taking it input as a if stream. Now if in one input 1, we have to take the input from that file, so we have to take the process ID and process memory location. These are the two inputs. See, two inputs we have to take. So while means the loop will go from input till process ID, then process memory, and then again it will be executed till we go to the last line. Then we are defining a vector called process, and then process pushback, means in the process we are pushing first the process ID, the first variable here, means 0 will be pushed, and then process pushback process memory size, and then this 500 will be pushed into the process vector, and then p size dot pushback. Now this process vector will be pushed back to the p size. It is also a vector of vectors. We have declared it in the first part. See, p size, it is a vector of vector int. It will store information regarding each process. So now what all information we stored for now, the process ID and the memory size for that process, and then we are pushing it into the p size vector. Now input 2. Now if ptrace as an argument is not set, again it is a file type, so if stream, and then if it is not valid, then valid ptrace file, and then input 2. Again we have to take two arguments, process ID and process memory location. Same process, only we are process memory location access, we are defining a new vector. In that we are first pushing the process ID, then process memory location, means here this 0 will be pushed back first, then in the process memory location 361. Now we get a memory location access which have two two integer types, process ID and process memory location. This is a vector. Now we will push this vector in the ptrace vector. Now ptrace, again we have defined it earlier, it is a vector of integer type vectors. So we are pushing this. Then for this, in the ptrace we will have 55 elements. 55 vectors will be stored in ptrace. Now we are checking whether the third argument is declared or not, which is size of pages, argument 3. Now we are storing it in the size of pages variable, which we declared here, size of pages. Now we have taken it as a input as a string, so string to integer conversion we are doing it and storing it in the size of pages. Then if it is less than or equal to 0, then we are passing a error message that please input a valid positive integer for size of pages. Then we are checking the validity of the fourth argument, which is our page replacement algorithm. Then again we are storing it in a is variable ISS, which we have declared it previously. Then if it is not set, then again a error message is displayed, and if it is set, then we are printing it to check whether it is the same which user have entered. And if it is not equal to FIFO or LRU, we are implementing two algorithms. So if it is different than these two, then a error message will be displayed, please input a valid page replacement algorithm, because we in our system we have only these two page replacement algorithms, and it will return. Now if it is proper, then it will be stored in page replacement algo. Now we have all we have done. Now we have to create processes. We got the information regarding how many process and the process size. So now we have to make the processes. Now we have to loop all the process sizes and create a new process object and push it to process list. Now process list, as we have seen, it is a vector of processes. What we are doing, we are getting the size of each process. Process memory size is equal to p size. Here we have stored p size, and then its second element. First element is the process ID, we want the size only, so second element means the index starts from 0, so the second element is 1, so p size means 5, so 0 to 4. Through each process we will loop this for loop, and this will get the size. And in the process list vector, we will push some processes, new process. See, we are making the object of the process class declared in process.h. So what all arguments we need to pass there? Process ID, process size, and size of pages. So we'll pass that. Process ID means I, here 0 0 1 1, like that. And then process memory size, which we have extracted from the p size vector. And then size of pages is same for every process, that is 5. So we will pass this. Now here we are making objects, means what all is happening at the back end. It is being the size, process ID is given to the process ID variable, size is given to size. We are calculating the page size for that process and creating that many number of pages for that process. Everything is happening in this one single line. We are creating new process, means we are also calculating the number of pages required for that process, and also making those many number of pages in this one. And all the process information is stored in a process list vector. Now we are going to initialize the virtual memory, means we are going to push each process page table. Here also, now the pages are created in the process, we are also making a page table. Now virtual memory will contain the page table of each process. So now here we are going to do that. So how? So we'll take the loop from 0 to the process list size. Now how many processes are there? 5. So it will be from 0 to 4. Then the next we have the memory size required for each process, means from 0 to how many it will go. means the page table size. It will be memory size, the total memory size is 400 divided by the size of pages. Now what is the size of pages? 5. 400 divided by 5 will have 80, and then the process list dot size means what is the process list, how many we have, 5. So again divide by 5, 16. 400 is the size of pages is 5 means 80, and then process list dot size divide by again 5 means 16. So 0 to 16 each process will have these many rows. That process will have those many rows. So now process list dot I means the first 0, the zeroth element from the process list means the first process. From that we are getting the page table of that process, and we are assigning its valid bit as 1. Its valid bit as 1. Now what is meant by valid bit? Valid bit is 1 if it is in the memory. So we are giving the valid bit as 1, and then we are pushing it in the virtual memory. Push back. Then again the page table is pushed back into the virtual memory. Then the main memory frames. How many frames will be created in the main memory? So our main memory frames will be memory size divided by size of pages. Again the same. We have 400 main memory size divided by size of pages is 5. So it will be 80. And then the number of frames per process. So main memory frames are 80 and number of processes we have 5. So 16 number of page frames for each process. Then initialize equal number of page frames for each process into main memory. Then the frames we will initialize. Again we are looping through all the processes. Then we are making a double-ended queue of page type, which is called the frames, because in main memory we have frames. So we are making your frames. Then it is a double-ended queue. So now again the num frames 16 for each process we need that. So we are storing it in the frames DQ virtual memory 0 process, and then each page of that process, it will be stored in the frames. And then in the main memory we are pushing those frames, means the main memory will contain all the frames of all the processes, and then we are clearing our frames double-ended queue. Now here now the virtual memory setup is done, main memory setup is done. We have created all the processes, we have created all the pages which we will require. Now the work is to implement the algorithms. Now if the page replacement algorithm is FIFO, first in first out, it will match the string. If it is first in first out, then the first in first out function will be called. We are giving the function, while calling the function we are giving two arguments, size of pages which is 5 and the number of frames. So this algorithm will be implemented, and later on the page swaps will also be displayed in the console. Then if it is LRU, means least recently used, then that algorithm will be called and the page swap number will be shown. Now let us see what happens in these two algorithms. Here the first we'll discuss first in first out. What happens in this algorithm means in this function, first it will print us to check whether the proper algorithm is only called in first out. Then we have to write our output in this output file. So it will open that file, fstream fout.open. We are going to give the name of our output file here, and then cg means from where we have to write our output. We are going to erase the previous contents of that file and write the new content from the beginning. So we have given this statement. Then we have the PID is the process ID. then the memory locations, and then the free location in the frames, means free locations in the main memory, we will check that. And then the requested page, which page is next requested. Now here first for loop ptrace dot size, means this it is stored in the ptrace. So ptrace dot size, in this case it is 55. So this function will be called, this for loop will be called 55 times, because we need to check each and every job, 0 job 361, 0 job 362, in this way. So now 0 job means ptrace, the first PID will be stored to PID, means this 0, ptrace 0 element contains this 0, then ptrace first element contains the memory location, means for the first it will contain 361. Then requested page is 361, but in our virtual memory the size of one page is 5, so we need to calculate that which memory requested page is on which, our memory location is on which page. So we will do that by, we know the memory location, virtual memory location. So it is 361, this is 361. So that memory location minus 1, this memory location minus 1, because we are our index starts from 0, so we are taking minus 1. So 361 divide by 361 minus 1, 360, divide by our page size is 5. So the page, the same memory location in the virtual memory is on page 72. So the requested page is 72. Now debugging print statement. These statements will be printed in the output file. The size of page is 5, iteration number, we are, means how many times this function will be called, so that is the iteration number. Memory location, it is requesting this 361 memory location, this 361 memory location. And then size of process, the size of first process 0 is 500, so 500 will be printed. And then getting PID, means which process, so we want 0th process, and which page number, we have calculated the page number as 72, so the page number is 72, this page number we are requesting. So let's check whether it is being checked or not. The same, see, size of process 5, iteration number, first time it is iterating, so 0, then memory location 361, size of 0th process is 500, and then requesting page number 72, we calculated it right. Then now for, we have got the page number, but we need to check that whether that page is in the main memory or not. If it is already in the main memory, then we don't need to swap the pages, but it is not in the main memory, then we need to swap the pages. So for the requested page, it will check whether the valid bit is equal to 0. If the main page is here in the page, we have declared that if it is not in the main memory, then it is 0, the valid bit. So if it is equal to 0, then we are going to print page is not in memory. See here, it is printed page is not in memory, and then we are going to swap. So for swapping purpose, we will check whether the main memory have some free space. So if main memory size is less than the number of frames for that specific process, if it is less, then we will just push back our requested page into that main memory. But if the page is, there is no free space, then we will remove the first in first out, means what, we'll remove the first element which we have entered in our main memory, and add our new element. So it is a double-ended queue, so the obviously the first element will be in the front. So we are just, first we are assigning the pages valid bit as 0, means it is not in the main memory now, and then popping the front element, means removing that page from our main memory, and then pushing back the requested page in the memory from the back side, means it is the recently used, we are pushing it back. And then this function is done, so we are printing swapped page see, swapped page is printed on in the output file, and then we have to maintain a counter how many pages are swapped. So we are incrementing that counter, and then the requested page valid bit is assigned to 1, means it is in the main memory. Now we have swapped it, so now it is in the main memory. Then now this happens if the page is not in the main memory, but if it is in the main memory, then simply we are just printing pages already in memory. See, now here same page number is requesting, so that page is already in the memory, it is printed already in memory. Now this was all about our first algorithm, first in first out. Now the second algorithm is least recently used. We'll loop through all the trace files. Again, it will loop through all the trace files, check whether that memory location is in the memory or not, and if it is not in the memory, then it will check whether the main memory have some free space. If it is have, then the page will be added to the main memory. If it don't have, then swapping will be performed. So we same variables are declared here, same process happens. Then it checks whether the valid bit is 0, means it is in the memory or not. If it is there if it is not there in the memory, page is not in memory will be printed. Same process happens as the first in first out, because it is a double-ended queue. So the first element, the element at the front, will be the least recently used, because it is in the first, it was added in the memory very before, so it is not used. So we are doing the same thing, we are converting the valid bit of the front element to 0, then popping that front element and then pushing the requested page. Then prints swapped page, and page swaps is incremented, and the requested page valid bit is assigned to 1. This happens if the page is not in the memory. Now if the page is already in memory, in first out, we simply printed page already in memory and leave it. But in least recently used, what we do, although the page is already in the memory, now for example, if there are 10 frames and the page is found at the 5th frame and we are using it again, so it will be on the 5th frame only, but least recently used means we are using it again, so we have to remove that page from there and add it at the last, so that it is the recently used page. So for that we are checking that this page is there on which location in the main memory, means main memory PID J means the process page ID, and then we are its page ID, whether it is equal to page ID, the requested page ID. We are checking through all the memory locations, and then when we find that memory location, we first find that memory location, we store it in the MRU location, memory location, then we erase that memory location, main memory PID dot erase. What we are erasing, the main memory location dot begin from 0 plus the memory location, means it is at 5th location, then 0 plus 5, begin is at 0, 0 plus 5, we are going to erase the data at the 5th location. Okay, and then pushing back the requested page at the last, because it is the recently used page, so we are putting it at the last, and then we are printing page swapped at the last of memory, because it is the recently used page. So this was all about both the algorithms. We have checked the first in first out algorithm implementation. Let us run it again. So for example, first in first out, it is taking 11 page swaps, and if we run it again, so now here if we run it again by least recently used LRU, again it is taking 11 swaps. So this was all about virtual memory multiprocess operating system. Thank you.